Alright, recursion. Recursion is when a method calls itself. A recursive method is designed to solve a particular problem, and when called it will do a little bit of work on the problem, only to come up with an easier version of the same problem. Each time it arrives at a simpler version of the original problem, it calls itself to solve the problem, because the method was in fact written to solve that problem. Rules for writing recursive methods. The first rule is the method must have a base case. A base case is usually the simplest form of the problem that, when reached, will terminate the method from recursing further. Your second rule. The method must be recursive. It must call itself. That's kind of what recursion is, so that one makes sense. The third rule is a little bit weird. The method must solve the problem. So I don't really see why this is a rule, and it's the easiest one to forget. Because if you write a method to calculate something, it should, let's say you were writing a method to calculate a sum. Well, when it's done, the sum should have been calculated, and that's what it did. So this is kind of, well, of course, the method should do what we set out for it to do. That's kind of just as a general rule. I don't see why it's a rule for recursion. Benefits and disadvantages. Recursive solutions tend to take less code and be easier to read and write than non-recursive solutions. This doesn't mean we should use recursion for everything. For most things, recursion just doesn't even make sense. But there are some complicated problems that we're going to cover in the future, in which recursion will be simpler than doing it with loops. The disadvantages of recursion. The disadvantages of recursion are that recursive solutions tend to take more space, so it's going to use more of your computer's memory, and it tends to be slower than non-recursive solutions. Usually there's a trade-off. If something takes a lot of space, it's fast. If something's fast, it uses a lot of space. Recursion is just across the board bad. It wastes a lot of space, and it runs really slowly. So you're like, why would we ever do it? Well, when a recursive solution happens almost instantaneously, even though it's a few milliseconds slower than something else, who cares? To us, it's instantaneous. And if it wastes a little bit of space, who cares? As long as it's not wasting so much space it crashes our computer. But recursion is slower and wasteful, so usually we don't use it. But there are some circumstances in which the recursive solution is vastly easier to code than the non-recursive solution. Alright. The recursive power method. So I'm just going to show you an example. We're not going to write a whole lot of recursion in this unit. We're going to mainly practice determining the output of recursion. But let's go ahead and see what the power method would look like if it were written recursively. So we're just going to make a really simple power method. So let's just see. Public static int power. I know. I have difficulty drawing really pretty with the mouse. So int, there's two things we need to know about the power: the base and the exponent. So comma int, I'm just going to call it expo. So the first thing we're going to cover is the easiest form of the problem. The easiest form of the problem would be if the expo is 0. If you take anything to power 0, you get 1. So return 1. Otherwise, we need to do a little bit of work on the problem only to come up with the same problem. So it would return our base multiplied by the power of the base to the exponent of 1 less. Expo minus 1. And I'm going to show you the idea of this. So I'm going to do an example. So let's go down here. If we have 2 raised to the power of 3, what's going to happen is we would like to say, well, that's really 2 times 2 raised to the 2nd power. Then you're going to say, well, that's really, well, 2 to the 2nd power is 2 times 2 to the 1. You say, well, 2 to the 1 is really 2 times 2 to the 0. Then you'd say, oh, 2 to the 0, I know that one. That's 1. So this would really be 2 times 2 times 2 times 1. And that's how it calculates. So 2 to the 0 is 1. So that fills in for 2 to the 0. So then 2 times 1 is 2. That will finish giving us a result of 2. So then it's that result, which is 2 times 2, that'd give us 8. We take that result, sorry, 4, not 8. 2 times 2 is 4. We take that result and multiply by the 2, and that would give us 8, and we'd return 8. Evaluating recursive methods. We're going to use substitution to evaluate recursive methods, and we're going to see this in a couple examples. Odds are I won't be able to finish this slide set in this video because I'm going to run out of time. But let's go ahead and get started. Here we have a simple method. Sorry, we're just trying to find out what the result of test 10 is. Now I'm lazy, I'm not going to write test, I'm just going to write T10. Sorry. So T, parenthesis, 10. We're trying to figure out, well, if we called test 10, what would happen? So we'd look at this. A is 10. Is A equal to 0? No. So it would return test A divided by 3 plus A. So T, A divided by 3, is 3 point who cares? Because it's an int, so it truncates. So 3 plus 10. Then we want to know, well, what is T3? T3 is equal to, well, let's see, our A is now 3. A, is it 0? No. So we do test divided by 3. So we do T1, 3 divided by 3 is 1, plus 3. We need to know what T1 is. So our A is now 1. Is A equal to 0? No. So we go down here. And we have test 0, because 1 divided by 3 is 0.3, and we truncate it, so we get T0 plus A, which is, A is 1 right now. And then we say, oh, well, T0, what is T0? 3. And now we finally got to a point that we can now plug back in and figure everything out. So, oh, that's a 1. Let me mark it up. I didn't know if it was a 1 or a 3. So, 1. So now we plug in for T0. We plug this in to be a 3. 1 plus 3 is 4. So everywhere we have T1, we can plug in a 4. 4. 4 plus 3 is 7. So everywhere we have T3, we can plug in a 7. And now we know that T10, or test 10, is equal to 17. Alright, mystery 5-3. Choose our pin, and we'll do M5. Sorry, mystery 5-6. I don't know why I said M3 or 5-3. So mystery 5-6. Let's see. Is A less than or equal to 1? No. Is B less than 3? No. Is A bigger than B? No. So we have to do the else. That's going to be mystery of 5, 3 times 3. Now we have to figure out mystery 5-3. So M 5-3. So M5-3 is equal to, let's see, is A less than or equal to 1? No. Is B less than 3? No, it is 3. Is A bigger than B? Well, yes it is. So we do mystery. Three. And we multiply that by 2. Now we need to figure out what mystery 3 is. M3 equals, let's figure out, is that less than 1? No. Is B less than 3? No. Is A bigger than B? No. So we do mystery. So M3, 0 times 3. Then we say M3, 0 equals, and now we say, is A less than or equal to 1? No. Is B less than 3? Yes. So we return A plus B. So 0 plus 3, we return 3. So we replace this up here with 3. 3 times 3 is 9. So we write down 9. If we know M33 is 9, we plug in a 9 right here, and we get 18. Then if we know that M53 is 18, we can plug in 18 here. 18 times 3 is 54. So we get M56 is equal to 54 as our final answer. Alright, so starting this one out, let's go ahead and change this to a less than, because that was supposed to be a less than for this problem to be at all interesting. So T x, y, 8. First thing we try to figure out is x less than or equal to 6. No. So what we have to return, this is going to be equal to a, b, so same data, x, y, 7, plus t, y, x, because now they're in the reverse order because we did BA. And that's going to be a 5. So first, let's figure out how this one works. So T, x, y, 7 is going to be equal to T, x, y, 6 plus T, y, x, 5. And now we got to figure out the remainder of these. So let's start by figuring out this one, which is T, x, y, 6. X is less than or equal to 6, so this one's already done. So we just concatenate y, or a and b, which is x and y. So that one's done. Now let's figure out this one, because we know this one terminates. Oh, it looks like we're running this one twice. So once we run this next one, we'll know all the answers. So T, y, x, because they're in reverse order, 5, that's less than or equal to 6. So in this one, we get yx. So now let's just go ahead and slowly run these. So tyx5 gives us yx as a result. We concatenate that with the results of xy6, which is xy. So the total result of this guy is going to be x, y, y, x as text. So we take that and plug it in up here, x, y, y, x, plus yx5. yx5 gives us yx, so yx, and then we concatenate these together to get x, y, y, x, y, x. And this is all text, and if we want to know what text xy8 returns, we would get this result, x, y, y, x, y, x. And that's it.